Our next speaker is M Kotiuga from Rutgers University, and she will tell us about the first principle study of ferroelectricity in samarium nickelate with intercalated hydrogen. As soon as the screen will go on. Good.
Great. Okay. Good morning. Thanks for the introduction. Thank you to the organizers. As was introduced, my name is M Kotiuga. I'm at Rutgers. I work with Karen Rabe, and I'm going to be talking about ferroelectricity and samarium nickelate with intercalated hydrogen. So first, just to give you an idea of what hydrogen-doped samarium nickelate is compared to samarium nickelate, it's an electron-doped structure where you intercalate the hydrogen in a reversible process, and this is due to the fact that hydrogen-doped samarium nickelate is an ionic conductor. And through this process, you can actually dope at extremely high concentrations of electron onto the nickel. So when the hydrogen intercalates, the electron comes off the hydrogen, localizes on a nearby nickel, and you convert a nickel 3+ to a nickel 2+. So there are some cartoons in this talk, and when any of the octahedron become darker, it's because this is showing an extra localized electron. Experimentally, what you see is that you get a huge change in resistivity as you intercalate the hydrogen. So here we go through about 7 orders of magnitude change, and then once you take the film out of the hydrogen-rich environment and put it into oxygen, the hydrogen will reversibly come out. Along with the change in resistivity, you also see the sample become transparent. So you can see words behind now this picture. So I just want to point out, we've added more electrons to samarium nickelate through this process, and we've made it more insulating and transparent. So at low concentrations of hydrogen, can we use the position of the hydrogen and what happens to the local structure to create a polar structure from samarium nickelate, which is nonpolar, and can we make them switchable? I'd like to point out this is not the first time someone's looked at making a ferroelectric from an ionic conductor. So there were transitions in ionic conductors to ferroelectrics seen going back to the 80s. So the bulk of my talk, we're going to first talk about some pristine properties of samarium nickelate to situate ourselves, then the microscopic picture of electron doping, what happens to the electronic structure, and then moving on to when we look at the explicit hydrogen, how this changes and actually creates a polarization, and then how we can at least predict maybe a switchable state. These calculations are done in a pretty standard fashion using VASP. Because samarium nickelate has a PBNM or P21/N structure, you have a 20 atom unit cell with 4 nickel per cell. And this hydrogen dope structures we'll be looking at is 1 added hydrogen into this 4 nickel cell. So again, the main goal I want to get to in this talk is looking at a switchable polar state that is not only based on the inclusion of hydrogen into the lattice, but the fact that we have electron localization and an actual just purely electronic dipole in the structure. So some of you might be familiar with the family of rare earth nickelates. They have a very well-known metal insulator transition that occurs for all of them except for lanthanum nickelate. Going through this transition, the structure changes from PBNM to P21/N. At room temperature, which we have mostly studied this material, samarium nickelate is an insulator, but it doesn't show a large charge disproportionation. So this topic of charge disproportionation and the insulating structure is very well studied, maybe not very well agreed upon, but that's not what I'm going to be focusing on in this talk. So, as I said, the pristine samarium nickelate at room temperature and low temperature has a P21/N symmetry. This means that we have 2 inequivalent nickel sites in our 4 nickel unit cell. In this case, even though we have 2 inequivalent nickel sites, all the octahedral volume are equivalent, and there is a Jahn-Teller distortion. Because the nickel is in a D7 configuration, we end up with magnetic moments that are all equal and about 1 Bohr magneton. So representing my unit cell with 4 nickels in a slightly cartoon-ish scheme, I'm going to be showing also the occupied nickel EG electrons. So in the D7 configuration, you have 1 EG electron. So here this is showing the two different sublattices of the nickel and they each have one Eg electron in the pristine state. The accompanying electronic structure, we see a small gap, and this is occurring between the Eg states of the nickel. We do see a very large hybridization with the oxygen states. So here I've colored in the remaining unoccupied nickel Eg states. And so we see that for each sublattice, you have 3 then times 2 remaining Eg states, and the remaining gray density of states you see around it is the part attributed to the oxygen. So as we add electrons, I'm first just going to add an electron with a positive background. This can be done in VASP just by increasing the number of electrons in the calculation. When this happens, we see a marked shift in the density of states, and the number of bands themselves are now different in this region right above the Fermi energy. So what's happening is this nickel now has an extra localized electron. This octahedron is about 13% larger, and we see the magnetic moment doubles. If we look at the associated density of states with this nickel, we see now there are only 2 unoccupied Eg states, and there is this state that has moved from the conduction band below the Fermi energy. So the remaining density of states stays roughly the same. The slight splitting is due to the fact that we've broken some symmetries. But our overall gap hasn't changed. However, we can see the number of states in this conduction band has reduced in this intermediate doping state. So just to give you a quick summary of what happens if you fully dope samarium nickelate, in this undoped structure, we have this small gap. It has 4 bands, 1 for each nickel in our unit cell. And in that intermediate doping structure, the added electrons localize 1 at a time. 1 band from this conduction band is moved into the valence band. This is not a rigid shift as we're doping this. Finally, when we fully dope it, our old conduction band is completely occupied. It's moved into the valence band, and our new conduction band is really about 3 eV above the Fermi energy. And so what's happened is we've rearranged the bands and opened a new gap that gives us this very insulating state. So going towards adding explicit hydrogen into the structure. Because of the octahedral tilts present in the PBNM or P21/N structure, where you put the hydrogen really makes a difference. So here I'm showing you the low energy structure of the hydrogen. You see that it likes to sit in a tetrahedral space where the octahedra can't towards each other. If we compare this to just simply moving the hydrogen below to the tetrahedral space where the octahedra are now canted away from each other, we see that this is already 100 MeV higher in energy. Also, if we look at the inequivalent oxygen site along the c-axis, because there's an in-phase rotation along this axis, you don't end up with a tetrahedra. So you get a different space where the hydrogen is coordinated, and this becomes even higher in energy. So going forward, this is going to be the type of structure we focus on. So keeping this hydrogen in this area where the octahedra are canted toward each other. So as before, when we added an electron, we see that the added hydrogen provides this electron to the samarium nickelate. Now, instead of just a general positive background charge, we have pretty much a proton sitting right here in our structure. So the magnetic moment of this nickel is again doubled. We see a similar volume increase. However, before, the volume increase was quite uniform. There was nothing breaking the symmetry and distorting the octahedra. But I'll touch on this in a second. I'd also like to point out that the change in electronic structure is remarkably similar to just having an electron and a positive background charge. So if you care just about the electronic structure, the actual position of the interstitials is not so important. As I said, you get a very distorted octahedra due to the hydrogen that now is sitting next to it. So if we're now looking in the AB plane, so imagine looking from above, the hydrogen likes to be opposite to this long bond of this nickel-oxygen octahedra, which is present because of that Jahn-Teller distortion I mentioned earlier. So we can actually easily visualize this electron localization by comparing the charge densities of different calculations. And so we can see that there is an electron depletion around the hydrogen, and it accumulates on this nickel-oxygen octahedron neighboring it. So here I'm showing a contour plot that's along the 1-1-1 plane that pretty much cuts along this hydrogen-oxygen bond. So the electron is localizing on the nickel-oxygen octahedra. It's not just on the nickel alone. And we get a polar structure that is not just due to the position of the hydrogen. We also have an expansion of the associated nickel octahedra. And because of the electron localization on this, we have this charge-ordered structure now. So we have a purely electronic dipole as well that is roughly an electron times the bond length, the nickel-oxygen bond length. So we end up with an overall polarization of about 27 microcoulombs per centimeter squared. And it is not in a trivial direction. So I'm trying to orient you in the direction of the polarization. So it's going from the center of the octahedra towards the hydrogen. So we have this relatively large component along the c-axis, and then otherwise it kind of remains along the 1-1-0 direction. So how do we construct a switchable state? So as I said before, the hydrogen likes to remain opposite to the long axis of the nickel that has become nickel 2+. So here in this structure, I'm just showing the one layer that has the hydrogen in it. So in that case, half the nickel are nickel 3+, the other half are nickel 2+, because now this is in the next unit cell. So if we want to create a structure where we move the electron from this nickel to here, we have to switch the ordering of this long and short axis. So looks something like this. Now our other sublattice is nickel 2+. The one that originally had the electron is now nickel 3+. Unfortunately, if your AB plane is not cubic, there's a difference in energy between these two structures. So in relaxed samarium nickelate, this is around 100 MeV. So going forward, to make a switchable state, we're going to strain this to STO and have this cubic in AB plane. So making samarium nickelate films on STO or strained to STO in our calculations, we see they have a very similar relaxed c-axis. Even though these parabolas look like they have slightly different minima, they're pretty close. And the scale here is about 1 MeV. So if we have this orthorhombic structure, we can switch from one to the other by linearly interpolating the structures. It remains insulating throughout. We have an energy barrier that's a little high, about 200 MeV. And we can see clearly that the magnetic moment switches between the single electron, e.g. electron, and the double electron. So finally coming to the polarization, because the position of the hydrogen doesn't change, the direction of the polarization along this c-axis is relatively constant. However, in the 1-1-0 direction, it does flip. So we end up with a switchable polarization of about 23 microcoulombs per centimeter squared. So like to come to my conclusions. So I've discussed how we can change the structure of SNO using added hydrogen, which causes electron doping, and the electrons actually localize on one nickel and are not itinerant in our structure. We've studied just one hydrogen added into a 4-nickel unit cell, and this gives us a polar structure, and we can have a switchable state with samarium nickelate with this intercalated hydrogen constrained in a cubic in-plane situation, constrained to the Laz parameter of STO. And this gave us a switchable state where the polarization remained along about the 1-1-0 direction of the PB&M cell, which is the 1-0-0 or 0-1-0 pseudocubic direction. So I'd like to thank you guys for your attention. I'd like to thank members of the Rabin Vanderbilt groups, especially Cyrus, who you're going to actually hear from in a few talks. And again, thank you for your attention and getting up so early.
Okay, questions?
So in your calculation, it looked like you used a G-type magnetic order.
Yep.
The nickelates exhibit an E-prime type.
Right.
Do you know the sensitivity of the polar structure or the charge order that you see on the magnetic order?
Yeah, there's... So first off, to get the E-type, you need a very large unit cell. So we looked in the 4-nickel unit cell, we looked at a whole bunch of different types of magnetic orderings. In terms of the electron doping and the changing of the band, overall like qualitative changing of the band structure, there's no difference. Once you get to fully doped structure, you see the same behavior, and when they do magnetic measurements of the fully doped structure, there is no long-range magnetic order. So in that case, we decided not to focus a lot on the magnetic order. I find in the calculations themselves, if you have, the nickel always wants to remain in this high state, high spin state due to the Hund's coupling, but then otherwise it tries to minimize its overall magnetic ordering. So if you have a G-type original ordering and you add now 2 electrons, it's going to try to put the electrons on nickel so that you still have an antiferromagnetic state. If you do this with A or C, you get a similar result.
Any other questions? So I have one question. So for this reversible hydrogen going in and out, I mean, what kind of temperature and pressure conditions do you need for that to happen?
So they can do this at room temperature. It just takes a little longer. Often experimentally, they do this around, I want to say like 100 Fahrenheit. So the metal insulator transition of samarium nickelate happens at around 104 Celsius. So they do this doping below that transition. So it will, but then once you've intercalated the hydrogen, it is stable in ambient conditions. Also, they've tuned, I think, the growing conditions for the samarium nickelate to have these films that exhibit a good metal insulator transition in our switchable. And I forgot to mention, so the experimental motivation and the group we've been working with on samarium nickelate generally is the Ramanathan group at Purdue.
Okay, so let's thank the speaker again.